Got an exam tomorrow? Need to cram the entire chapter on solutions like right now? Well, you've got 5 minutes, and honestly, that's all we're gonna need. Let's do this. Okay, we're gonna go from the absolute basics all the way to the big, tricky ideas, and we're gonna do it fast. So first things first, what actually happens when you dissolve something? What is a solution? Let's start with the absolute bedrock definition. If you get this right, I promise, everything else just clicks into place. Okay, there are two key words here you've got to lock in. First, homogeneous. That just means it's perfectly, uniformly mixed. You can't see the different parts. And second, non-reacting. This is crucial. The substances are just hanging out together. They aren't actually forming a new chemical. Super simple, right? The solute is the stuff you add, and the solvent is the stuff you add it to. So salt and water, salt is the solute, water is the solvent. And for our purposes, we're just talking about one of each. So, how do we talk about how strong or concentrated a solution is? Well, that's where concentration comes in. And there are two key terms you absolutely, positively cannot get mixed up. Now listen up, because this is a classic exam question. Molarity with an R uses the volume of the entire solution. But what happens when you heat things up? They expand, so the volume changes. Molality with an L uses the mass of the solvent, and mass doesn't change with temperature. That makes molality way more reliable for serious lab work. All right, let's get into the rulebook. There are a couple of laws that predict exactly how solutions are going to behave, and we'll start with how gases dissolve in liquids. This shows a really simple but powerful idea. The more pressure you put on a gas, the more of it you can force into a liquid. The perfect real-world example? A can of soda. It's packed under high pressure to keep all that carbon dioxide dissolved. The second you pop the top, psh, the pressure is released and the gas starts escaping. That's Henry's law right there. Okay, now for liquids. Rolf's law sounds way more complicated than it is. All it's really saying is that the more of a substance you have in a mixture, its mole fraction, the more it contributes to the overall vapor pressure above the liquid. Basically, more stuff means more vapor. That's it. But does Raoult's law work perfectly every single time? Not quite. And this is where we get to the really interesting difference between a perfect theory and the kind of messy real world. Here's the deal. In a perfect, ideal solution, all the different molecules get along perfectly. The attraction between them is exactly the same. But in the real world, in a non-ideal solution, some molecules might attract each other more strongly, or they might kind of repel each other. This changes how they behave, and that's what we usually see. All right, we've arrived at the main event. This is arguably the most important part of the chapter. These are 4 properties that all change just because you added a solute, something like salt or sugar, that doesn't evaporate easily. And here is the single most important insight you need to have. It doesn't matter what you add. It only matters how many particles you add. 1,000,000 salt particles will have the exact same effect on these properties as 1,000,000 sugar particles. It is all about the numbers game. Now, you have to see how these first 3 are connected. It's like a domino effect. When you add a solute, those new particles get in the way. They make it harder for the solvent molecules to escape into the air as vapor. So the vapor pressure goes down. And if the vapor pressure is lower, you have to heat the solution more to get it to boil, and you have to cool it down more to get it to freeze. See, it's all connected.
But wait, there's one final brilliant twist. All our math so far has made a big assumption that when we put one particle in, it stays as one particle. But what if it breaks apart?
This is the key question. Think about it. When you dissolve something like table salt, NaCl, in water, does it just float around as a single NaCl unit? The answer is a huge no, and figuring this out was a massive leap forward. So for something like salt, NaCl, the moment it hits the water, it dissociates. It breaks apart into 2 separate ions, a sodium ion and a chloride ion. So for every 1 unit of salt you thought you added, you actually get 2 particles in the solution. This little correction is called the Van 't Hoff factor, and we call it I. For salt, I equals 2. And here is the beautiful, elegant fix. We just take all those formulas for the colligative properties, and we multiply them by I. That's it. This one simple step accounts for the true number of particles floating around, and suddenly our calculations match reality perfectly. It's brilliant. So what's the big takeaway from all this? It all comes down to counting the particles. That single simple idea, is the science behind why antifreeze keeps your car's engine from boiling over or freezing solid. It's why we throw salt on icy roads in the winter. It's not just some abstract theory. It's literally how the world works. And that is your entire chapter in 5 minutes. You got this.